Okay, so we are finally to our last astronomer we have to know for our test, and that astronomer is Isaac Newton. So, Isaac Newton, we have to know a couple things about him. We are going to have to know a little math about him. We're going to have to know Newton's law of gravity, and we're going to have to know his three laws of motion. So, Isaac Newton, he was a mathematician, he was an astronomer. He did some brilliant things with optics and physics as well, and that kind of all ties in together. He was also a really, really kind of strange guy. He would he he was actually a professor when he lectured at his university. He would actually almost lecture to himself. A lot of his students said they had no idea what he was talking about, and he would just talk out loud about things that he found interesting. And he was pretty much trying to solve problems that he thought about. He didn't really care what his students was actually thinking. And a common misconception with Newton is that he learned about gravity from an apple falling and hitting him on the head. That probably never happened. He probably watched an apple fall one day, and that gave him an idea about gravity. But like I said, he's a brilliant, brilliant guy. He actually discovers his laws of motion and law of gravity, and he writes all this stuff down. But he's a very unorganized person, and he actually ended up losing all his work. And after losing it, he didn't feel like going back and writing it again. But later on in his life, a friend of his, another astronomer, came to him and asked him if he could figure out this idea about what gravity is, this force that's acting on the planets. And Newton says he's already done that. And his friend actually tells him to rewrite his information that he can remember all from his head, and he does that. And the book he writes is revolutionary. And in that book, he talks about his law of gravity and his three laws of motion. So we're going to go over those laws here. His first law, so Newton's first law, it's called the law of inertia. Make sure you know that. That will definitely be on your test. So you've heard about his laws in physics. I'm not going to spend that much time with them because you should know this stuff. You've had it before, but we need to know that what this law states. So it's the law of inertia. And I always like to think about like driving in a car. If you're in a car for Newton's law of inertia, if you're going the same speed as a car, you can't really tell it's moving. But what happens if like a car darts out right in front of you and your car hits that car? What does the car want to do? The car wants to stop. And what do you end up doing? Well, you end up flying, and if you have your seatbelt on, it saves you from hitting the windshield and flying out of the windshield. But if you don't have your seatbelt on, you actually might fly out of the windshield. That's Newton's law of inertia, which says, an object in motion will stay in motion, an object at rest will stay at rest unless acted upon by an outside force. So that's his first law. This is the book he wrote. Right here, it's called Principia Mathematica, Mathematical Principles. Um, you know, so in this book, that's where he talks about his three laws and gravity. So we're going to go over those here. So in 1684, Newton is 42 years old, comes up with his idea of three laws of motion, and he actually, in his book, he says that Johannes Kepler is actually the reason he's coming up with these ideas. He hears about Kepler's work, and he tries to put forth a scientific explanation for the math behind Kepler. So that's what he's doing here. So three laws of motion and gravity. And these laws, Newton's laws and Kepler's laws together, they explain the motions of every heavenly body in the universe that we know about. So this is revolutionary at the time. And remember, this happens after Galileo. So it's Galileo, and then Kepler, and then Newton. Those three astronomers are really what changed our worldview of going from geocentrism to heliocentrism, which again means sun-centered. So here's his first law of inertia. So think about this tennis ball here. So this tennis ball, when it's hit across the net, the tennis ball, there's two motions which the tennis ball wants to do. It's going to travel in the direction it was hit, so it's going to travel this direction, but it's also, you have gravity pulling it downward, so it's also going to travel this direction as well. So it's going to go along the horizontal and then along the vertical, this direction this way, and then down because of gravity. So it's going to make it kind of arc until it gets hit by an outside force. And so you have, this is Maria Sharapova. She's about to hit the tennis ball, and when she hits it, she's going to put a force on it, which is going to make it go in the other direction. So instead of going down in this way, it'll probably go a little up and this way. So that's law of inertia. Object in motion will stay in motion. Object at rest will stay at rest unless acted upon by an outside force. So another example, think about putting something on a table. You put something on a table, like a ball, just put a ball on a table, take your hand off of it, and it doesn't move. That's because now there are forces on the ball, but those forces are equal to each other. So if you put a ball on a table, you have the force of gravity pulling it downward, but you also have the table's force pushing upward on the ball, which keeps it from moving. Now, if you push the ball, give it a little push with your finger, the ball will start rolling, and that's because you've introduced an outside force. So you have actually given the ball a force. So again, that's Newton's first law, law of inertia. And we'll do some problems with this later on, probably later on this week, but that's his first law. Second law is the law that has an equation you have to know. And so this is just a long statement about his second law. I'm going to keep it nice and simple for you. His second law says force is equal to mass times acceleration. That's the formula you need to know. Force is equal to mass times acceleration. So force, think about what force is. We've learned about in physics. So force is measured, the unit for force is a Newton. The abbreviation for a Newton is a capital N. Mass, the unit of measurement for mass, we're going to say is kilograms, little k, little g. And then acceleration, unit for acceleration is meters per second squared. Please don't mix up acceleration with velocity. Acceleration is meters per second squared, whereas a velocity would be just meters per second. Acceleration is meters per second, which is meters per second squared. So force equals mass times acceleration. So let's look at these two images here. So here we have a dragster, and then here we have a tank. So example I like to use is, well, which one of these can, put forth more force? And it just depends. A lot of people will say, well, the tank can put forth more force. Well, it depends on how fast the tank can move. Dragsters can move very, very quickly. They can accelerate to over 300 miles per hour, pretty fast. So they have a very high acceleration, but a very low mass. But you need both mass and acceleration for force. So high acceleration, low mass still gives you a great force. A tank, depending on its top speed, it's going to have a huge mass, maybe not the best acceleration. But since its mass is so large, it's still going to have a huge force. So force equals mass times acceleration. That is Newton's second law. First law is Newton's law of inertia. Second law, force equals mass times acceleration. Okay, Newton's third law, we've all heard of his third law, but a lot of people actually get confused on his third law. So I'm going to give you a couple examples with this. First thing we have to know, though, is what Newton's third law says. So Newton's third law says, for every action, there's an equal and opposite reaction. For every action, there's an equal and opposite reaction. So over here in the picture on the right, there's an example of the space shuttle blasting off. And let me just talk about this for a minute. I actually have a bunch of students, it's a common misconception. Well, I don't know how common, but it is a misconception. A lot of students actually think that the reason this rocket goes up is because you have this stream of energy blasting off of the ground, pushing it upward. That is not actually what happens in a rocket taking off. You actually have a nozzle here on the rocket, and the force of the fuel burning pushes through that nozzle right here. So that force is pushing downward, causing the shuttle to move upward. Force pushes downward through the nozzle right here, causing the shuttle to move upward. So if that energy from moving through that nozzle is great enough, going downward, that makes the shuttle go upward. And this is old. We obviously don't use shuttles anymore, but I used to love the shuttles as a kid, so I just like this picture. That's an example of Newton's third law of motion. For every action, there's an equal and opposite reaction. Another example, I'm going to give you a couple examples here. Think about if you're driving down a car, driving down the highway in a car. So you're driving on a highway in the car, and then you see this little fly, and you see it flying in the air, and then it looks like it's going to come straight for your window, and then it hits your window. So how scared are you when you see that fly flying, and then you can tell that that fly is actually going to hit your window? Do you guys ever like drive, going down the interstate like 65 miles an hour and you see a fly and it's going to hit and you scream, no? Obviously that doesn't happen because, you're not afraid that that fly is going to hurt your car. So why is that? So which one can exert a greater force when a fly hits the window of a windshield of a car? Is the fly going to exert a greater force, or is the car able to exert a greater force? So think about Newton's third law here, and you'll realize that neither of them are exerting a greater force. The fly and the car are actually exerting the exact same force. So that's why, when a fly hits your windshield, it doesn't break the windshield, because the fly is so small, it's got such a small mass and a very small acceleration, that the car doesn't have to hit the fly with very much force. So just because the car can hit with a greater force, it doesn't take that much force to move the fly. So it only hits with the same amount of force the fly can hit the car with. Now, think about, you're driving down a country road and all of a sudden a deer jumps out and hits your windshield. What's going to happen then? Is it going to be the same effect as a fly hitting your window? Obviously not, because a deer has more mass, and since it has more mass, it can do more damage to your car. Now, is the car going to hit the deer with more mass than the deer can hit the car? No, it's going to be the exact same amount, because Newton's third law says there's always an equal and opposite reaction. So the force of one is equal to the force of the other in the opposite direction. That's what Newton's third law of motion says. All right, the last thing we need to know about for this unit, we have to know about Newton's law of gravity. And there is a formula we have to know. So in this next slide, I'm going to give you the formula. I'm going to talk about what this is. So the formula is a big F of G equals big G times M1, M2 divided by R squared. So we're going to go over what exactly this formula, what exactly these letters in this formula mean, and how to calculate each of them. So this is Newton's law of gravity. So it starts by saying that every object in the universe attracts other objects. So it doesn't matter how big the object is. If there is an object with mass, all objects have mass. So with mass, there's going to be a attraction of gravity between two objects. Doesn't matter how far apart they are, there's still going to be an attraction of gravity. Now that attraction between them, which would be the force of gravity, does depend on the size of the objects, which deals with the mass, and the distance between the objects, which deals with the r squared. So the gravitational force between two objects depends on their masses and the distance between them. So when we say the distance between them, we always measure the distance between them by the distance between the two center points of the objects. So it's always from the center of the object, because that's where gravity starts from, is the center. So these three laws plus gravity are what produce the Copernican solar system model, which Kepler's laws were able to show, but Isaac Newton's laws of motion are able to explain. So Kepler shows the Copernican system, and Newton can explain the Copernican system. So let's go over an example with this formula here. So there's the formula. F of G is equal to big G, M1, M2, divided by R squared. So this slide just tells you what each of these objects is. So big F of G is equal to the force of gravity, which is measured in newtons or newtons per kilogram. Big G is always going to be equal to big G. It's called a gravitational constant. So it's 6.74. It keeps going on, 6.7408. I'm just going to use 6.674. So 6.674 times 10 to the negative 11th meters cubed divided by kilogram second squared. So it's a long unit there. We're not going to really, that's going to be a given to you. So gravitational constant is given to you. And we're going to be, and the example I'm going to show you how we get rid of some of these units to make a smaller unit for when we're solving for the force of G, which again is measured in newtons or newtons per kilogram. So M1 is equal to the mass of the first object. Mass, we're always going to measure in kilograms. M2 is the mass of the second object, also measured in kilograms. And then R squared, that deals with the distance between the center of mass of both objects. And it's measured in meters squared. So it deals with distances between the two center masses of the objects. So let's try an example here. So calculate the gravitational force in newtons between Earth, which has a mass of 5.972 times 10 to the 24th kilograms, and the Moon, which has a mass of 7.348 times 10 to the 22nd kilograms. Now the average distance between the Earth and Moon is 3.844 times 10 to the 8th meters. So anytime we're dealing with distances, when we're dealing with gravitational force, we're going to use meters. So we're not using AUs here, we're using meters. We're not using miles, it's meters. So first thing we have to do is we have to write down our formula. So f of g is equal to g times m1, m2 over r squared. So then we're going to plug in what's given to us. And always when you're plugging your numbers in, don't forget your units. You always want to include your units. Always, always, always. So we're trying to figure out, what are we trying to figure out, guys? We're trying to figure out the gravitational force. So we're trying to figure out f of g. So we say f of g equals, we plug in gravitational constant, 6.674 times 10 to the negative 11th meters cubed divided by kilograms second squared. We're going to multiply the gravitational constant by the two masses. So m1, 5.972 times 10 to the 24th kilograms. m2, 7.348 times 10 to the 22nd kilograms. And then we're going to divide that by the average distance between the Earth and Moon, which is 3.844 times 10 to the 8th meters. That's down here. Now don't forget we have to square that. It has to be squared because the formula is r squared. So before we continue here, we're going to go ahead and try to get rid of some of these units. So if we look, we have meters cubed up top here, and we've got meters squared down below here. So we can actually go ahead and get rid of the meters squared down here, and that just leaves us with 3.844 times 10 to the 8th squared. And if we got rid of the meters squared down here, that means that we're only going to be left with meters up here. So we have 3 here, we got 2 here, 3 minus 2 is equal to 1. So that is going to be meters. And if you look, we're dividing by kilograms second squared. Over here, we're multiplying by kilogram and kilogram. So these are on top. This is on bottom. So we can actually take away this kilogram and this kilogram. Those will cancel out because this is on top. This one's on bottom because it's being divided. So that leaves us with meter per second squared kilograms. So kilogram meter per second squared. That will be our unit. So I took away those units, and this is what you get. So the unit for force is kilogram meters per second squared, which ends up becoming a newton. That's what a newton is equal to. So there's the meter. We took two meters away from this one. So that leaves us with meters. Kilogram, these 2 kilograms cancel out, so it leaves us with second squared. No unit there because that was canceled. And then we have kilogram here. So the force unit is kilograms meters per second squared, which is equal to a newton. So now all we have to do is plug these numbers in our calculator. When you're plugging these numbers in your calculator, make sure you're using a scientific calculator. Make sure you know how to use your calculator. This is the bad thing about me not being able to be there with you. I can't see what you're plugging in, so make sure you know how to use your calculator and the way you do scientific notation. So if you want to plug numbers in with scientific notation, you're going to plug in on your scientific calculator 6.674, and then you're going to push the EE button, the big E button on your calculator, and that's equal to times 10, and then you're just going to plug in negative 11, and you're going to do that with each and every number. Anytime you're doing scientific notation, use the EE button. That's the easiest way to do it. So if you plug all this in, go ahead and try it and see what you get. So you can pause and then try it and see what you get. I'm going to go and tell you the answer coming up right now. So we get the force of gravity, the gravitational force, is equal to 1.98 times 10 to the 20th newtons. So plug all that in. And again, don't forget to square this number before we divide. and you get 1.98 times 10 to the 20th newtons. That is the gravitational force between the Earth and the moon. That's just one example. We'll probably do some more examples of these later on. But again, for today, I just want to show you the one example of how to use the gravitational force formula. So Newton comes up with these three laws of motion: force of gravity, gravitational force. And remember, the force of gravity on the Earth is equal to what? What's acceleration due to gravity? You should remember that from physics as well. So acceleration due to gravity is equal to 9.8 meters per second squared. That's the acceleration due to gravity. Not the force of gravity, but acceleration due to gravity. There's Isaac Newton for you. I already told you earlier that he's kind of a strange guy. He liked to keep to himself. He really he loved learning. He loved, learning new things and education. He just loved it. He didn't really have too many friends because a lot of people say he was a very strange fellow. Definitely kind of weird. But I mean, remember, he's the guy that invented calculus. And so he loved math. He loved astronomy. He also invents the reflecting telescope. We're going to talk about that when we get to light and telescopes. And he did a lot with light and optics. So because of Newton's ideas, the Copernican model becomes widely accepted. Again, Kepler is able to show the Copernican model, and Newton is able to explain the Copernican model. So this works for any new body that we have discovered even today, until we get to start talking about black holes. But other than that, all objects that we see in the solar system, they all conform to Newton's laws of motion with Kepler's laws of planetary motion. So with that, guys, we have finished our notes for our first unit. So we're going to end up testing sometime next week, and we're going to have a quiz on Thursday. And I'll tell you what's on the quiz during class today.